All right, so general idea today is it's the last class before the exam, so I wanted to kind of give more review. We did review Monday, but we got a little bit more now. I told people whoever showed up would get to ask for certain questions, and I've been asked to do two different things as of now. The first one I was asked for was another Kochov loop, one we haven't seen before, and then I was asked to do something from chapter 20. So I'm going to start with the Kochov loop, which I'm going to make everything disappear for a split second to, dear God, my background is crazy. I was grading the exam, so I have a lot of stuff on that screen. Not the screen you saw, the other one. But I just went and acquired this loop that I'm sure this figure of 18.27 doesn't mean that it's blatantly plagiarized from something, really. So, when solving a Kirchhoff loop, what you're going to do is you're going to be usually finding multiple currents. And the current will change at each junction. Now, I don't think I've done this one before. This looks new to me.
Yeah,
Um,
it looks new.
okay. So what you're going to do is when you want to do a Kirchhoff loop, is you're going to first have to basically label your currents. And when you label your currents, you want to not only say, you know, which current is where, but also which direction. And so you just kind of arbitrarily pick them. Now, I kind of hate this actually because they just put in numbers and didn't label their resistors. So I'm going to draw this again, and I fully acknowledge that you can't see where I'm drawing it right now because I'm drawing it underneath, because I'm going to get rid of that picture in a split second. Because I find that if I start plugging in numbers right away, I'm more likely to mix things up, especially with a 20 and a 20 and a 10 in there, just mixing up the two. Okay, so we'll come back to the values. And oop, that's not what I wanted to do. We'll come back to these values in a little bit. But there's the picture. I just switched to numbers. Really should have switched my V's, but whatever. So the first thing I'm going to do is I'm going to label my currents. Now, I normally label my currents by the resistors, saying that I1 goes through R1, I2 goes through R2, I3 goes through R3, just to make life simple. It's not required. You don't have to do that, but it's just, you don't want to mess yourself up more than you have to. But more importantly, I have to pick the directions. Now, current likes to go from negative to a positive on a battery. It won't always be able to do that, but it likes to. So I'm going to guess my currents as that I1 goes this way. And I'm saying this way because it's through the battery. I'm going to say I2 is also to the right. And I'm saying that again because the battery is pushing. And I'll say I3 is to the left. Now, if I had, these are arbitrary things. I'm predicting that because it seems like it probably is that way, but it doesn't matter if you're wrong. Just pick directions, whatever they are. Once you have your directions, you can start doing your loops or your rules. And the things you should do is one junction rule and two loop rules. You could do three loop rules. It's just going to be a lot harder math-wise. And the junction rule says at any spot the current in equals the current out. You see, if I was to continue my arrows, I1 comes down into this junction. I2 comes into this junction. But I3 leaves that junction. And that'll be my junction rule. The junction rule states the current in equals the current out. And since I1 and I2 go into that, and I3 leaves it, that means I1 plus I2 equals I3. After you get that, you can make your loops. Now, for making your loops, you normally have a few different choices. But you just need to make a closed loop, because for any closed loop, the total potential drop is 0. Now, keep in mind, and since I have the textbook open, because that's where I pulled this problem from, I should be able to steal a figure that I had stolen from it before. Wow, that is going slow. There we go. Fine, do that. See if I kill. But for a closed loop, the total potential is 0. And what we're going to do is we're going to say that if you go in the direction of the current over resistor, you subtract IL. If you go opposite the direction of the current of resistor, you add IL. If you go from negative to positive on a battery, you add the voltage. If you go from positive to negative on a battery, you subtract the voltage. And you just follow that through the loops. Now I have 3 options for loops: the big one, the bottom, and the top. I'm going to start with the big one because I feel like it. I have no better reason. Actually, I'm going to do all 3 loops. You only need 2, but I'm going to do all 3 just to make sure we're on the same page. So the big one. I'm going to start here. Well, sum of potential is 0. We got that much. I'm going to go up, and I cross over V1. I'm crossing over V1 from the small side to the big side, so that's going to be a positive V1. I then cross over R1. My current, I said, was to the right, and I'm moving to the right. So I'm going to subtract R1, I1. I'll come down, and then I cross over R3. I'm crossing over R3 in the same direction of my current, so I'll subtract R3, I3. And that's my loop. The bottom loop, I'll do the same idea. I'll start here. I go over the battery V2, and it's in the positive direction. I then go over R2. I then go over R3. Now that's enough to solve it. As I said, I'm going to do the third loop just so you can see it, because the third loop is actually the most complicated loop here. And since it's kind of a little complicated, I'll show it just to make sure you can see how to do it if things get weird. But there's no need to do it really. The top loop, if I start here and go up, I say, okay, I equals 0. I go over the battery. I go across R1, I1. But if I keep going around, if I do this loop, you're going to see that the current's to the right and I'm moving to the left when I make this loop. That means I'm going against the current in my loop. If you go against the current in your loop, you don't subtract the resistance, you add the resistance. If I keep going, I then take this battery and I'm going from the big line to the little line. I'm going from my positive to my negative. So I'm going against the battery too. So I wouldn't add the battery, I'd subtract the battery. And that would be my last loop. Any questions so far?
Nope.
Now, as I said, I'm not even going to bother with this loop. I'm just going to be like, whatever. I got these 3. That's good enough. And how I like to do it, there's a lot of ways to do it, but what I like to do is I figure out what current is in all terms. If you look, I3, 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 it shows up everywhere. And so what I'm going to do is I'm going to, my computer just said it wasn't sharing I'm still sharing my screen, right?
Yeah, you're still sharing.
Okay.
Or, well, I see the paper, I mean.
Yeah, you see this. The thing that says I'm sharing this just went away. So that was interesting. We'll just say we're good. Okay. I like to find the current that's in all 3 spots, I3, I3, I3. And I take my loop rules and I solve for everything that isn't that. So for this top equation, I'm going to solve for R1. And I'm going to kind of do this over here. I'm going to add R1, I1 to both sides. Saying R1, I1 equals V1 minus R3, I3. Sorry, R3, I3. I can then divide both sides by R1 and say I1 equals V1 minus R3, I3 over R1. Now, normally I don't recommend plugging in numbers right away. With these, it sometimes makes the math less messy. I don't have to plug in the numbers right now. I could get away if I don't. But let's plug in the numbers in an effort to simplify the math. And so I'll say that equal to V1, which I keep looking down at my paper, but it's not there, it's on my screen. So V1 is 20 volts minus O3, which is 20 ohms, I3 over O1, which is 30 ohms. So 20 over 30 is 2/3 is 0.667. So I have 0.667 amps minus 0.667 I3. Meanwhile, I'm going to solve my other loop and do the same thing. All I3s in all of them, so I'm going to solve for the piece that isn't I3. I'm going to add all 2 I2 to both sides. Divide both sides by all 2. And once again, I don't need to plug in now. I could just shove these into there, but I'm going to plug in now, trying to hope that it lessens how ugly the math gets. So V2 is 10 volts. O3 is 20 ohms. And O2 is 5 ohms. Well, this one comes out nicely as 2 amps minus 4 I3. See, now I have an equation for I1. I have an equation for I2. And I'm going to put them into this equation. I'm going to say I1, 0.667 amps minus 0.667 I3 plus I2, 2 amps minus 4 I3 equals I3. So that ends up being 2.667 amps minus 4.667 I3 equals I3, or 2.667 amps minus, or equals, I'm going to add this to both sides, 5.667 I3. 2.667 divided by 5.667 is something ugly. And I can get I3. Once you get one of them, you'll plug that number in. So I'll go back down to here and say, okay, that means this equals 0.667 amps minus 0.667 times 0.471 amps. Minus. And then do the same thing here. 2 minus 4 times that number, which I'm not going to bother showing me putting the numbers in just because I'm out of space. But you should be able to get the idea. That's the process. Now, grading wise, almost all the points is going to come from this here. Very little points comes from the final answers. Usually I also ask for the direction. When I ask for the direction, go back to what you predicted. If you get a positive answer, what you predicted was right. If you get a negative answer, just swap what you predicted for what you say it is. Any questions?
So like, let's say this did come up negative. When you say swap, like which ones are
So
you
like if I
swapping?
found I2 was negative 0.118. If I found I2 is negative 0.118, I'd say, okay, that means it's to the left.
Okay. And when you switch one of them, do you have to switch all of them, or
No.
okay,
So
just the negative one?
here, give me a second. I'm going to open something else up. I'm pretty sure What? That's not what I wanted. I'm pretty sure one of the problems I did in the packet, the example problems, I purposely did backwards. +1. Nope, not that. There's somewhere that I did one with it backwards. Maybe it was last semester's exam. Okay, last semester's exam. So this is the problem I did Monday. When I solved for I2, I got a positive number. When I solved for I1, I got a positive number. When I solved for I3, I got a negative answer. And all that meant is, okay, that one was in the opposite direction. Wait, I3, oh, I3. So that means, okay, I3 was backwards. I drew it going up then left. I got a negative answer. That means it's going right then down. I asked for the direction through the resistors, so that's downhill. That's all it is. That being said, if the first one you solve for is negative, when you plug it into the earlier equations, make sure you plug it in as a negative value. Does that make sense?
Yeah.
Okay. So, why am I using my left monitor? It's just to confuse myself, I think. The other thing I was asked for was something exam worthy from chapter 20. Okay, chapter 20. Really, it's going to be mostly dealing with this, this, and how they relate to each other. That's what I'm going to be doing question 20. The type of thing I will put on an exam will be, let me Ooh, I still have tea from lunch. Will be probably something where you have a series of point charges and you need to find the force. This is one of the ones we did on the homework where I said, okay, we have this point charge, this point charge, this point charge. What is the electric field right here? Or I might say we have this point charge, this point charge. What's the force here? It's going to be something like that. And what they're going to deal with is probably a whole bunch of vectors. It might get simplified. If you look at last semester's exam, that some of the things canceled out. It might not. I might also just go straight to using this and not having to go as deep. So let's go through one. And actually, you know what? Why don't I do this one? Right? This was on the homework. Does that sound good? I think Tim asked for this, right? Is that okay?
Yeah, that'll work.
Okay. So, let me get the figure up because so many things open. Come on, download faster as you keep getting to see my background. Okay, so this one said, what is the electric field here, halfway? And it says it's an equilateral triangle. Okay. If I want to find the electric field, before I look for the electric field, I should think about the direction of the electric field and say, you know, from each force, each charge, which way is the electric field? And here's the idea. Electric fields point away from positive and they point towards negative. And so for each one, I would say, okay, Q1 is positive. Its electric field is going to point straight down. Q2 is positive. Its electric field is going to point away from it. Q3 is negative. Its electric field is also going to point towards it. And so that's what my electric fields are going to look like. That my electric field in Y is going to be negative my electric field from charge 1. My electric field in X is going to be my electric field in 2 plus my electric field in 3. That I can just logic that without even going into these equations. And once I have a general idea is the direction of my electric field, and start with the direction of electric field. Start with your free body diagrams. It's all about the free body diagrams still. Even literally, like right now in Physics 1, I'm teaching PHYS and teaching free body diagrams. So you are exactly one semester year type thing away from learning these free body diagrams, right? Fourth week of classes when you learn Physics 1, fourth week of classes, we're using them again. They don't go away. And what I'll do is I'll say, okay, that's my EX and EY. Let's solve for each value. My EY was negative E1. That means it's just going to be negative KE Q1 over all squared. Now, there is a problem there with solving for all, but I can get all because, well, I happen to remember it's going to be 0.5 times the square root of 3 over 2. But if you don't have that memorized, this is 0.5, which means this is 0.25. Sorry, I said square root of 3 over, yeah, square root of 3 over 2. And I can say, okay, Pythagorean theorem. 0.5 squared equals 0.25 squared plus whatever the hell we're looking for squared. And you can do that math. You're going to get 0.5 times the square root of 3 over 2. But you can do that math. For the other one, we'll just say the same idea. That it's going to be KEQ2 over all squared, but this all is going to be 0.25. And the other one, it's going to be KEQ3 over 0.25 meters squared. Thing is, I'm never going to ask what's the X component, what's the Y component. I'm going to say what's the magnitude and direction. And this will give you the X and Y component, but no one gives a shit about the X and Y component. Once you have your components, you can find magnitude and direction, where the magnitude is the square root of EX squared plus EY squared, and the direction is the inverse tangent of Y over X. Do you want me to plug in numbers, or is that okay like that?
That's fine like that.
Okay. As I said, this one, I'm trying to make it not super ugly. Like some of the other ones we did were like, where's the one? So I'm trying to find one we did on the homework that was just kind of a pain in the ass. Like I don't want the exam to take too long. So those of you who have had me before, you might remember my rule from last semester. I don't give you an exam I can't do in 1/10 the time. When these get complicated with vectors and you have to find the component of every single vector, they can get time consuming. My goal isn't to be time consuming, it's to test what you know. So either I'll do something where the vectors are nice straight lines, like this one. I'm trying to point at the picture, but the picture's on the screen. I guess if I do like this, pointing at the picture, either something like this, where the vectors start in nice straight lines, and then you get a component, or I would do something like what was on last semester's exam, though obviously won't be the same as that, where the vectors didn't start out nice, but everything canceled down to reduce real nice. Because if you remember last semester's, come on, scroll. Look, nope, that's why I wasn't scrolling. Was this guy, where like these are at angles, but the y's canceled out. I'll do one or the other. I'm not gonna make it a real bitch. There was like one of the ones on the practice problem was a square, with the electric field in the middle, even if I do that, they all had balancing Q's. So like all of the Y's canceled on it. Because it was like this when you did it all. Just look at the exam power and packet. I'll do something like that. Now, all of the ones I just did though were electric field. None of them were force. If I did it with force, all that means is there would be a charged particle at this spot. That I would just say, you know, there's a charged particle here. What's the force on it? But the logic is going to be the same. You just have to add another piece in. I mean, I could go more crazy. Like there was one on the homework saying, what's the electric field need to be to keep us charged suspended by gravity? That's also fair game for an exam. Because you say, okay, the force up has to be QE, force down is mg. I expect you to remember that. Oops.
That's gonna be like that's like the problem I had you help me with on the homework with the bar.
Yep. Yes. Yeah. I try to shy away from using physics 1 stuff on the exams because it's been a long time. So I try to use physics 1 stuff as little as possible, as physics 1 equations. But I assume you remember the force due to gravity is mg. That's about as complicated as I try to get. I'm not going to suddenly expect you to remember your kinematics equations or remember. I mean, I guess I still have you remember F equals ma, but F equals ma is also simple. You know, I don't expect you to remember the buoyancy equations off the top of your head. Anything
Yeah,
coming
I
back
don't
from
want to
physics
do.
1, I'll either recover it or just I'll stick to the very simple. And really, the very simple, I think I don't do anything other than F equals ma and the weight of something is mg. I don't think I do anything else from physics 1 anytime soon. And when I
Yeah, I don't want to
do,
use the. I
say
don't want to
again.
use the ideal gas law for a charged particle.
Oh. Now, if I go into something that you need the physics 1 stuff, I make a big deal about it. When we get into relativity, I'm going to touch on physics 1 stuff again a little bit because we're dealing with velocities again, but it'll be quick. And momentum will come into play one more time. But once again, I'll cover it in detail then. Other questions? What else can I help with today?
I think that there was a problem from chapter 20 again where I wasn't really understanding. I think it was in the practice problem sheet. It had 3-point charges, and I think it wanted to ask about the force. Something like that, where they're not suspended or in any sort of like formation. They're just there. But I think that it was asking for magnitude and direction, same thing. Yeah, like that.
This one?
Yeah.
Okay. This guy, if you want to find the force, what I'm going to do is I'm just going to start with figuring out the directions. And I'll say, okay, which one to go? So it says no electric force. Okay, Q2 has no force. Okay, so we want the force on Q2. So what I'll do is I'll start by saying, you know what, I'm not going to do what I was about to do. This is 1, this is 2, and I'm going to call the middle one 3. And I'll start by saying, okay, what direction is the force from each one? Now, if I'm saying the net force on 2 is 0, I'm going to look at 2 and say 2 gets a force from 1, 2 gets a force from 3. The force between 1 and 2, they're both positive. It's a repulsive. Force between 2 and 3, one's positive and one's negative. It's attractive. And I'll say F equals ma, the whole right minus left, that F1 minus F3 must be 0 because the net force is 0. F1 equals F3. Does that make sense so far?
Yeah.
So now that I have that general idea, I can say, okay, force due to a charge. The force due to a charge is Ke Q1 Q2 over R squared. Well, I'm going to absolute value this because I already dealt with the negative sign in this vector format. And so I'll say Ke I did 1 first, Q1, Q2 over R12 squared equals KE, Q2, Q3 over R23 squared. I'm not drawing my absolute value signs just because it gets really ugly when I keep putting them, but know that I plan on continuing to absolute value. Oh, I can put them. Now it says, what's Q1? So I'm going to solve this for Q1. I'll first divide both sides by KE, which cancels them out. I will divide both sides by Q2, which cancels those out. And yeah, we're starting Q1. And I'll multiply both sides by R12 squared. This is actually fair to be on an exam, this problem. I could see me using this problem. And then it's just plug in. Which, what? There should still be absolute value signs. I dropped them. So 2 times 10 to the negative 9 coulombs, because I'm absolute valuing that. R12 is 20 centimeters. And R23 is 10 centimeters. So it's going to be 8 times 10 to the negative 9. Yep, 8 times 10 to negative 9. I didn't open the solutions, I only opened the thing. But it's the same idea. Yep, I was right.
Okay, I see how you got that.
What else can I help with?
Just one more quick question. So, I think it popped up on the homework, or no, it didn't. It popped up on, I think, the 5th question in chapter 20 on one of the practice problems. It was the one where the two protons were sort of, they had 2 different angles, and we made the free body diagrams for them, and they were suspended on a little string. Would we see something like that on the exam, possibly? It was the one where we
You
had...
meant this guy?
Yeah, that one.
No, that guy's a real pain in the ass.
Okay.
I mean, this is feasible, but this, well, I can go do it in my head real fast.
Yeah,
Oh,
where the angle...
okay, there's 2 charges going and an electric field. Yeah, no, this is a complicated problem because they each have a force attracting them, and they each have the force of the electric field, so that the free body diagram ends up being, sorry, I'm just doing this in my head real fast.
I have the notes.
Each
I can
one
always
has
just tell you.
tension, each one has gravity, then each one has the attractive force, then
With the
each one has the
QE,
force of the electric field, the QE, which is negative for the electron. And then you'd have to take this tension and split it into components. Yeah, no, that I wouldn't give that. That's just time consuming. It's a doable problem. Just physics 1, but I don't want to give you something that time consuming.
Just to clarify, when you ask for something like in chapter 22, you ask for the resistance of a wire and then the resistivity of the wire.
Resistivity. Yep.
Yeah, that's the inverse of the resistance, right?
No. Resistance of a wire is rho L over A. Resistivity is a property of a given material, and resistance is also based off the length and the area. I'm going to be honest, resistivity is not going to come up. My question from chapter 22 will be a Kirchhoff loop. so you won't need it. But resistivity is this rho value. It's just a physical property for any given material. Which I say it's this, it actually varies with temperature, but that, and I talked about that in class, that it varies with temperature, kind of weird, but you won't need to deal with that.
That's good to know.
I've said it a few times, Coach of loop.
Yep.
Can you do one more example problem from chapter 21 using capacitors?
Okay. So for 21, do you want like capacitors in parallel and series one? Because it's either gonna be something like capacitor in parallel and series, or it's gonna be something like potential and potential energy. Which would you rather?
The potential energy.
Potential energy. Okay, so potential or potential energy. And you know, I'll do a homework problem because those I'll find one that's about the right level. That's easier for me to find. Well, you know what? Hold on. I could also do this guy again. I'll do that. If I ask for the potential or the potential energy, and let's start with the potential. Sorry, let me do this in my head real fast. Yeah, let's start with the potential. If I ask for the potential, potential is KEQ over all, but is not a vector. This was the problem we did before, right? And before I said, what's the electric field at a point, electric field at the point right here? If I wanted to find the potential of that, I would literally just do KEQ1 over R1 plus KEQ2 over R2 plus KEQ3 over R3. 3. I keep trying to cube things apparently. You wouldn't worry about vectors. You just add them up. Now here I'd have to say Q3 is negative. I'd have to include that. You can't absolute value here, but you just add them up. And so it would just be KE, did I not grab the values for that problem? I didn't grab the values when I grabbed it. Just KEQ1 over, 1, 5 square root of 3 over 2, or 0.5, plus KEQ2 over 0.25, plus KEQ3 over 0.25. If I ask for potential energy is KEQ1, Q2 over all. Now, same thing, include any negative signs. But that would be, if I do that, that would be like I said, okay, there is another particle right here. Oops, that's what I wanted you to do. I wanted you to do this. Say, okay, there's another particle right here. What's the potential energy of that particle? And I would just say, that would be Q4 pi. I'd just say KEQ1, Q4 over all. KEQ2, Q4 over all. KEQ4, Q3 over all. Now we just add them up. No vectors, just add. On the homework, you did have ones like that. Here's one of them. I hate when it does that. Here's one of them. Where I asked for the potential at point A and B. And you just don't worry about vectors. You just KEQ over all in each one. Now, if I do a capacitor one, a capacitor would be the capacitors in parallel and series. That's going to be a little more involved. But you said that type, right?
Well, I guess I read it wrong when I wanted the potential difference. I was reading the question. I was looking at chapter 21, question 4 from the example problems that you gave us. And it
Hold
says
on.
the potential
Let
difference across each
me
capacitor.
You said chapter 21, number 4?
Yep, number 4.
Okay, that is with the capacitors. If you're going to do this, This is the whole thing where you're going to have to go and find the equivalent capacitance. And what time is it? 8 minutes? Ooh, that's going to be tight. That's going to be the thing where you find the equivalent capacitance. And then once you find the equivalent capacitance, you can say, okay, the equivalent capacitor has the same potential as the battery. And then you work your way back. Everything in parallel have the same potential. Everything in series have the same charge. And that's
It's
what I
almost
did.
like the opposite for resistance, like
Well,
with
resistors is the same.
Kirchhoff's.
Everything in parallel has the same voltage on a resistor. Everything in series has the same current on a resistor, which is directly related. Though what's different between a capacitor and series is that resistors in series add up, as opposed to capacitors, which in parallel add up. We got 7 minutes. Do you want me to try to solve through this in a rushed way, or?
No, that's okay, because I have it solved here. I think I got that.
And there is a video of me solving it, so.
Right.
So there's like 3 good things that came out of online. And I think one of them is I think I like having videos of my lecture so that if someone wants to look at something again, they can, or if someone misses a class, they can. It's the one thing that makes me kind of happy. Since they just told me today I'm online next semester too.
Yeah, I do like the fact that like when I'm doing homework and if I miss like I'm not as worried about missing like something during the notes.
Yeah.
I don't feel like I have to take down everything you say. I can actually listen to what you're saying more than because I can go back and
Yeah, no, I
check
think once I'm back in person, I'm going to keep my YouTube channel up and just like direct students to it if they have questions.
It's probably a good idea.
Yeah. I mean, that's the general idea. I'm not going to lie, the Kirchhoff loop problem is the most time-consuming problem on the exam. I tried to make it because I was trying to do randomized numbers. I made an Excel sheet that could solve for the Kirchhoff loop I picked, and I think I made it so the numbers always come out nice-ish. Like it may come out to a decimal, but it would be like 0.2 or 0.4. It won't be like 0.1387 times. I tried to make them all nice. The rest of it, I think, is pretty straightforward. It's not as fun as my normal exams. Physics 1, I always made it had a point to make every exam a pop culture reference. That's really hard to do with Physics 2. I worked some in those still. Struggling. But, yeah, it's not as easy to do. I don't know what else. Don't know what else to tell you.
With the numbers, how they're a little bit more nicer to work with. I'm studying for the MCAT right now, and when they talk about, you can't use a calculator. So when they talk about G, they just put it as 10.
Yeah.
And when they're talking about something like equivalent capacity, 5.
Yep. Not. You should try doing if you get into like high energy physics, like astronomy type stuff, it's amazing the approximations you make. Yeah, dope. That's a thing. I always go a little more exact. I stick to my G as 9.81. That's what it is. All right. I'm going to end there because it's basically 3:50. Hopefully this helped somewhat. As I said, I'll post this video that, let's see who watches it. I actually have, hold on a second. But I'm going to stop recording there.